Hi everyone, my name's Adam. I work for the Dfinity Foundation, and I'm going to talk about running Wasm on our replicated state machine, which is essentially a blockchain that we contribute to. And the purpose of this talk is a little bit different from some of the previous ones. I'm not really presenting research results. These are more sort of perspectives on how we use Wasm. We have some open questions and things like that. So it's sort of some new ideas. As I said, this is like a high-performance blockchain that we're contributing to, and we use Wasm on it, and it leads to kind of some niche properties or requirements or goals in how we use Wasm. So for the other industry people out here, I guess it's sort of a question does anyone else have some of these same goals or requirements? Are these things you're also interested in? Or for the researchers, maybe some of these things would be interesting research topics, maybe there are things you haven't considered that someone might be interested in before, that kind of thing. So like I say, Dfinity, we contribute to the Internet Computer Protocol, which is essentially a blockchain, and the idea is it should be kind of like a cloud service where you can run Wasm. If someone has any kind of computation of any sort, they should, if they can compile it to Wasm, they can upload it to our system, and we'll run it in a decentralized manner, securely, and across nodes that don't necessarily need to trust each other. So just an outline of what I'm going to say. First, I'm going to go over some of the basic principles of our blockchain, and a bit of outline of how it works, and then I'll get into some of these properties of how we run Wasm and how they come out of those principles. Okay, so so Wasm on the Internet Computer Protocol. So like I said, this is essentially just a distributed replicated state machine. It's running on a bunch of nodes. It's Byzantine fault tolerant, so up to 1/3 of our nodes can be malicious, and the network will still make progress. The nodes are owned by different legal entities. They're in different data centers, et cetera. They don't really need to trust each other. We provide some of the nodes, but only some of them. And so a state machine, I guess you guys know what this is, but basically we just have some given state and some inputs, and we have a transition function that defines how the state gets updated. And what does our state actually consist of? So in our case, the state consists of all applications that users have uploaded to the system. And these applications are mainly Wasm instances that are running with their attached memory and state. And so the global state of the state machine is essentially a collection of Wasm instances. The protocol, it allows for users to upload new applications or delete their applications or modify their applications, things like that. So the collection changes as time goes on. But I'm not going to talk about that part so much in this. I'm mainly going to talk about the how the state of a single application updates as we execute Wasm, and the state progresses. So in more detail, what does a user application look like? It has some WebAssembly bytecode. It also has some associated data, which is going to be like the memory of this Wasm module that's running. And the programming model here, it's based on the actor model. So basically, these different applications can send messages to each other and receive messages, and that's how they can call into each other. And also, users from the outside can send messages to individual applications to get data out, put data in, trigger some action, et cetera. And that's the general model of how this thing runs. So what does the transition function look like? Basically, somewhere within the state, we have a handful of Wasm modules, and some of them will have pending input messages. And the transition will consist of choosing some messages to execute, and then executing them by actually running WebAssembly, updating the memory of the WebAssembly module and other things, and possibly producing new messages, right? That will be application specific, whether handling of a given message triggers a new message to be sent somewhere else. So after we've made the transition, you possibly have some messages sitting in output queues, and you have some WebAssembly modules with new states. And each message essentially consists of a function on the targeted Wasm module with some input data. So you're basically just naming, the Wasm module will export a function by name, and you give that name and the ID of the Wasm module to send it a message, along with just some string of bytes, which is the input data. And then when I say handling the message, it's literally just executing that Wasm function, that exported function on the Wasm module. And as you can know in this example, some messages might not be handled. Basically, the transition is expected to run in some fixed amount of time. In our case, something like a second, like some fixed small amount of time. So depending on what's sitting in input queues, we may not be able to handle every message at a given time. And there's a scheduler built into the system which decides which messages we're actually going to execute. And so some may get handled and some may not get handled, depending on the situation. And so this is a bit more detail of what the associated state of Wasm module looks like and what we need to keep track of. So as I mentioned, we have the input queues and the output queues for pending messages that are coming in and new ones that should be delivered to other Wasm modules. And then in addition to that, we track the state of any globals that the Wasm module exports. And we also track the state of the Wasm memory itself, like the, we allow a single Wasm memory, and we track its state, and it can grow up to 4 gigabytes because we're still running 32-bit Wasm. And then on top, we also have this thing, which I call the stable memory, which can be quite large, actually 500 gigabytes, I think, in our current setup. And this is essentially like a block storage, basically, that the Wasm module can also use to store more data, and also for kind of longer-term storage, which I'll get into a bit more later. But yeah, you can essentially think of it like block storage. And so the state of any single Wasm module could potentially be hundreds of gigabytes. And as I said, we need to track it, and it also needs to factor into the consensus. As I said, we have a bunch of nodes that are all participating in the system. When we need to do transition, all the nodes will apply the transition function, get the new states of Wasm modules, and then they'll need to send some messages between each other to agree on the new state. And essentially, we need 2/3 of them to agree and have the exact same results for their Wasm modules. So of all the things we need to track, we need to track it to maintain the state, but we also need all the nodes to agree, and we need to be able to efficiently send messages around to conclude that they agree without sending the full hundreds of gigabytes or whatever. So what are the main kind of principles that govern how this works from what I've outlined? Or I guess first I should ask if anyone has any questions. Is there anything I need to clarify? Okay, cool. So one thing that pretty clearly comes out is determinism. Since we need to reach this consensus across all the nodes, this execution has to be deterministic. And in addition to that, we need to be able to charge for consumed resources in a fair way, right? There's a bunch of different users all sending in applications, and if people have applications that are doing a lot of work on the nodes, then they should be paying some higher amount. And if your application isn't doing anything, then maybe you don't need to be paying so much. Essentially you have to pay for how you use the network. And the third thing is isolation. Again, these applications are all coming from different users. And we mainly get isolation just for free from WebAssembly, although we do actually have an additional layer of sandboxing that we do ourselves, just like process isolation with SE Linux. But yeah, I won't talk about that one so much because WebAssembly just kind of makes it easy. And the last thing is we have this persistent state, right? These applications can potentially just run indefinitely and keep updating their state forever and ever. So, okay. So part 2, I'm going to go into some of the specifics of how this actually affects how we run Wasm. So yeah, the first thing is like coming from this determinism. Like I said, we need a determinism in how we execute Wasm, right? So all the nodes can agree on the new state. So one practical thing we have to do is we have to enable NAND canonicalization. Floating point operations don't necessarily result in the same NANDs when they do result in NANDs. And since we need to agree like bit for bit, that means we have to run this NAND canonicalization step. This is implemented in Wasm time, which we use, and we turn that on. We also can't really use threads, right? Because any kind of threading could lead to non-determinism. We do still care about float performance, though. Like we want our floating operations to be fast, because it should be for arbitrary computation. So like any user could like want to do floating point operations, and we still want them to be fast, even though we have to do this NAND canonicalization, which makes it worse. And people have more and more been requesting to do things like AI inference, right? And there are projects like WasNN or maybe similar things for doing AI inference or like GPU workloads or other hardware acceleration through Wasm. And if we want to make use of any of those things, we're going to need to figure out how this can be done deterministically and get deterministic results. And that is kind of an open question we have. So yeah, I don't know if anyone has any ideas about that, but I guess something like NAND canonicalization is not enough, right? Because like there could be all kind of threading going under the hood there, or who knows what else in terms of non-determinism. So this is still something we need to figure out. Another thing that comes up is we need a deterministic termination of messages and also deterministic fair charging. So as I said, like nodes or users need to pay for the resources they're using on the network. And so we need to meter application CPU usage so that we can charge them for the CPU usage that they use, and also terminate them if they run for too long. So essentially what we do is we do instrumentation to keep a counter, and we update that for each Wasm instruction. I mean, not like before and after each Wasm instruction, but we count each Wasm instruction. And these are weighted kind of by the execution time on our system is determined by various benchmarks and things. But it's obviously like very imprecise, right? Some Wasm instructions you can relatively well determine what they're going to cost on your CPU because they essentially should compile to a single CPU instruction or something like that. But other things can be much less clear, right? Like instructions that involve branching or like memory access or something, right? Depending on the page faults, could have like vastly different cycles that they take, and like could vary a lot in how they charge. So currently we just kind of do something static, and we make best guesses. And obviously this isn't going to ever be perfect, but I guess an open question is kind of like, to what degree can we like guarantee that our weighting is approximate to what is actually going on in the system. And I was going to say some other things about this. Oh, termination, I didn't exactly mention this before, but like similar to the CPU usage, right? Like, or similar to charging, right? We need to terminate just so that like some application doesn't go out of control and take over the whole system. We do run multiple applications in parallel, so like one application can't block everything else from making progress, but we only have some degree of parallelism. So we still need to terminate things. Our instrumentation we do by rewriting the bytecode, like we mutate the Wasm bytecode to include this metering. We don't use Walrus. We use a tool that I guess like our own thing, which is I guess similar to Walrus, but it's a bit less general, but it's quite a bit faster. We looked into using Walrus at some point, but it was a bit too slow for our use case. So, okay. Another thing here is tracking the Wasm memory. As I said, we need to track the state, and we want to do this in an efficient way. So basically, the way we store the state of the memory is we have a base file which represents the state of the memory at some like point in the recent past, and on top of that we have an overlay of dirty pages which were mutated recently, and we use a signal handler to detect reads and writes and make modifications based on those. So basically, Wasm time has a feature called host memory, where instead of just like allocating a block to use for the Wasm memory, it asks the application that's running Wasm time to provide a memory. So like we can map our own region with protections to enable the signal handler. And then when there's a read, we check if we should lazily load in one of these dirty pages. And if there's a write, we know that at the end of the execution, we're going to need to create a dirty page based off of this. And this allows us to like roll back all the changes if the Wasm module traps, and also efficiently get a summary of the changes that have been made from the written pages, so we can provide those in consensus. Yeah. And so something else we've been looking into is could this performance be improved by instrumenting the WebAssembly itself to include read and write barriers? This is something we experimented with a little bit and potentially could be good, but we're still not quite sure about it. So the basic idea here would be something like, inject an additional memory into the Wasm module itself to use as a bitmap or byte map and track which pages are dirty, or like which pages are dirty, and when you have writes, like mark to that bitmap, and when you have reads, like call into a host function or something to possibly load in a page lazily. Those are the ideas there, and it seems like they could be good, but this is still kind of an open question of whether it's really better for us. And then compilation. So by compilation, I mean kind of a two-step process here. We have the original Wasm module that is sent in by a user, and then we have our instrumentation to include this metering, like I described, and some other things. And that generates a new Wasm module, and then we use Wasm times compilation process, which generates essentially x86. And that's what gets executed, and the result of this gets cached on any machine that's participating in the network until it reboots or upgrades or something. And so by compilation, I mean kind of these two steps in this process. And so one issue here, one issue we have with the compilation is, there's kind of two issues. So one issue is that it's not deterministic when compilation is actually going to happen, right? If a user sends in a new application that they want to upload to the network, then obviously you're going to have to do this. If they send in a new Wasm module, you're going to have to do this step. But it could happen just randomly otherwise. For example, if some node participating in the network reboots for some reason, then this cache is going to get wiped, and it's going to have to recompile everything before it executes any messages. Similarly, the participation is always changing, right? Like nodes are joining and leaving, and if a new node joins, it's not going to have any of these cached compilation artifacts. So one, we don't know necessarily when compilation will happen, and two, even when it does happen, we don't really have a deterministic measure for the resources used. Like this instrumentation we do when we're actually executing Wasm, we can't really do that instrumentation for the compilation step itself. So all this means is that it just makes it hard to charge for the for the network resources used for compilation because it's happening non-deterministically. And so basically all we do right now is we just don't charge for this compilation stuff at all and just kind of assume that it's relatively fast. So we impose limits on our Wasm modules so that hopefully you can't just upload some gigantic one which takes forever to compile. That's what we do at the moment. So I guess one question would be could we do something statically to check better that a Wasm module will compile in some fast amount of time, right? Maybe we should use a simpler single pass compiler where we can, since we know it's just going to be a single pass, can we essentially statically determine what the compilation will look like in terms of time. Or another alternative here would be to actually make this compilation process deterministic so that the x86 artifact can be stored in the actual state of the replicated state machine, right? Like when I showed the state of the Wasm module before, like this compiled artifact wasn't there. Like we cache it as an optimization on all the nodes, but it's not part of like the official state, and so which is why it needs to be redone by every node that joins. But if we could actually like put the x86 in the official state, then when a node joins, it would be passed that information along with the rest of the state and could just use it directly without needing to do the compilation step itself. But one tricky part there is then it needs to be deterministic as well, because for consensus. And so, yeah, like at the moment, the Wasm time compilation isn't necessarily going to be deterministic, and like, you know, I don't see any reason why they would want to try to do that, right? That would be really tricky. One thing we actually tried in this space was doing the compilation, this whole compilation step inside of Wasm itself, because then we get the determinism of Wasm, and we got that working. Like you can actually now, if you wanted to, like take some WebAssembly code and use Wasm times compilation, run it within Wasm to compile to a to x86 or some other target, and it does work, but we lost out a bit on the performance because we couldn't enable threads for determinism, and without threading, the compilation is just like much slower. I mean, the threading doesn't do anything super fancy in Wasm time. Like it's just it'll just do multiple functions in different threads, but like already that was just too much to make it practically useful. Although maybe there's something more we can do in the future to figure that out. Like maybe some, well, I don't know. Yeah. Okay, and so the last one I want to talk about is how we persist state across Wasm changes. So as I said before, we have these two memories that we provide to a module. So there's the actual Wasm memory, which is just the memory defined by the Wasm module. And then we also have the stable memory, which you can read and write to like a block storage, essentially. And as I said, applications, they could just run indefinitely as long as you want. You can like upload it once and run it forever. That's obviously going to be a problem unless you like never write bugs or anything, right? So a user is going to want to update their Wasm module at some point, and at that point, what they can do is there's a hook essentially to take whatever information you need from your Wasm memory, serialize it to this long-term storage. Then you can update your Wasm module and read back whatever you want from this stable memory. And yeah, you can do it kind of all at once when you do an upgrade, or a lot of applications will also just keep the stable memory up to date as they're running so that they don't need to do a big serialization and deserialization step on upgrade. Oh yeah, sorry, I said that already. But there's also some other things that could go on here. So Motoko is a language that Andreas Rosberg actually worked on mainly for a long time, and it is a language that was made for running on our platform, and they are recently looking into the idea of just kind of stabilizing how they lay out data structures in memory in the heap, so that they could, in fact, just keep the same Wasm memory and upgrade a module, and then just keep using the memory that they had. I guess this is a bit tricky because you're kind of like, if you upgrade the compiler or something, you somehow have to guarantee it's going to be able to read old heaps from older versions of the compiler, and then you kind of have to maintain that for indefinitely. But yeah, it's something they're working on, and so that's an interesting idea. I guess another question I have is could using something like the Wasm GC proposal make this a bit easier? Because it kind of provides some structure already for you, right? You don't have to, if you create some GC structures, then Wasm is already telling you, you have an array or whatever, and maybe then you don't need to lock yourself into as many properties in terms of the layout of the Wasm memory itself, if you're using kind of the structure already provided to you by the GC proposal. which will continue to be supported. So yeah, that's another kind of open question of like, could you use this to allow your language to better reuse old states, even if you have a new compiler or something like that? Yeah, so yeah, that's about it. That's all I got. Yeah.
Do we have questions for Adam?
So the weighted weights of each instruction for the metering.
Yep.
How scientific are your weights? I'm wondering.
How scientific?
Like, so the context is in binary and optimizer and LLVM, all sorts of places, we need weights for instructions to guide optimizations. In almost all those places, it's just based on like vibes and good luck. So if you or anyone else here has actually done some science to find, you know, relative weights for the instructions, that would be super useful.
I see. I see. So, I mean, the weights are at the, we're waiting, okay, yeah, because you're talking about generative WebAssembly. Yeah, I mean, they are like scientific in the sense of like we have micro benchmarks, like we automatically generate Wasm modules with like big loops and, you know, doing the same instructions and over again, and then we like, you know, we actually run them and yeah, we use those number bits to base it off of. So yeah, they're scientific in that sense. Yeah.
Would you be able to share those numbers?
Yeah, it's on our repo. I can show you where they are. Yeah.
I guess these are only relevant for Wasm time, and I feel like that's a very different problem. It seems like it's a very different problem from the one in binarian, where it seems like those weights are fundamentally not attainable because you don't know the environment you're going to run in, your content is going to run in.
Yeah.
Unless you only care about one browser for whatever reason.
Yeah, that's a good point. Like, we do only run Wasm time with our own optimization level on x86, and that's all we care about, so, yeah.
On the other hand, if you're optimizing for Dfinity, you might want to use the exact weights and give them to binarian so that it optimizes perfectly for you.
That's a good point.
So I had a question about time.
Mm-hmm.
So is there any intent to allow deterministic time, like timers, timed events?
Yeah. So we do support that, and essentially each transition of the state is like a block which has a time fed in as part of the state. Like the nodes kind of agree, you know, when they complete a round, they like agree on what the time is essentially, and then you'll get that time. So time does work, and you can use that to like set timers and trigger other events at later points in time. But you don't get while your message is running, like time is not incrementing there. Yeah, I guess we could, you know, do some simulation of it there or something, but yeah. But you do get a rough current time from that, yeah.
There's a question on the Zoom, how to incorporate Wasm GC into Dfinity.
Yeah. I was actually just asking Nick about that before because, yeah, like if we wanted to support Wasm GC, this description I did of how we track the memory and with the signal handler and stuff, like I guess we need to do that for GC'd objects as well. And it sounds like, I guess hopefully the GC implementation in Wasm time could make use of just like a raw memory buffer, which we provide, and then hopefully we could treat it just as if it was like a regular memory, but it would be like secretly holding GC objects. That would be like one good way to do it. Yeah.
There's a question from Andreas. Go ahead.
Oh yeah.
Yeah, hi.
Hey,
I was just surprised that you did not mention the use of multi-memory you're now doing for the stable memory.
Oh yeah. I didn't really get into that. Yeah, that's a good point. Yeah, that was something we implemented a little while ago. So this this stable memory that I described, I said you use it like a block storage, and there's just like an API you call to read and write to it. It's our own one we made because like WASI didn't exist at the time, but I guess you could just use WASI APIs for reading and writing to a file or something, and it would work like that. And for the longest time, this was implemented like a normal host function. Like we kept the storage separate, and you'd call into that API, and we'd read and write from like this separate storage. But then as a performance improvement, what we realized you can actually do is make this stable memory an additional memory within the Wasm module, which we included instrumentation time. So users still like think it's a host like external API that they import and call, but then when we do this instrumentation, in addition to the metering, we add this extra memory and we replace all calls to the host read and write functions to new Wasm functions, which we also inject, which are just doing like essentially mem copies between your regular memory and this additional memory we've injected. So we don't support, like from the user perspective, we don't support multi-memory. You're only allowed to have one, but in our actual implementation, we're using it to do this. And we got a pretty good performance boost from that, yeah.
Does that mean that you are going to offer multi-memory?
We would definitely like to. The tricky part is just that, well, I guess to be honest, it's mostly just like implementation details, but like a lot of work in there, just because like, I guess the system was, like it was a bit built around like assuming that you have one memory per Wasm module, and if we then like want to support multiple ones, I mean, first there's a bunch of limitations, right? Now we need to kind of like limit the global memory somehow, and this state kind of assumes like we kind of have like a fixed file structure per application in the state, and now that file structure would like vary depending on how many memories you have. Plus, they could be like changing as the user upload, when they update the Wasm module. So it's just like, yeah, I think it's just like details kind of in that thing, but there are a lot, so I can't promise it anytime soon. But I think we would certainly like to at some point, yeah.
Okay, one more question at the back.
Yeah, kind of related to the first line of questioning. Why is there a large focus on like weighted instruction-based monitor, what do you call it, metering, and not a system-based CPU timer? Because like if all of your nodes are structured the same, could you use like CPU cycle timers to meter instead of like weighting Wasm instructions?
I think it would just be really tricky to make it deterministic.
I get you.
Yeah, I think that, yeah.
Okay, that answers the question.
Yeah.
All right, let's thank the speaker.